Thank you. So I'm presenting joint work with Malte Helmer, Jakob Nordström, Gabriele Röger, and Tanja Schindler, and we work on pseudo-Boolean proof logging for optimal planning. So the question is, what is optimal planning? In optimal planning, we consider planning tasks. They consist of a set of variables, an initial state, which is a subset of the variables, a goal condition, which is also a subset of the variables, and there are some actions that have a precondition saying when am I allowed to apply an action. They have an add effect saying when I have the one state and then applying the action, how would the successor state differ by adding some variables to it. It also has a delete effect, which is similar, saying from the state to the successor state, which variables would I lose on applying these actions. And they also have a cost. How much resources would I need to apply this action? And all of them together, they build a factored transition system. And a plan would be a sequence in this transition system from the initial state to one of the states that fulfill the goal condition. So in this example, it's very easy because it's just a two-dimensional Hamming cube, but we can extend it to more variables and get more dimensions, so to say. And here I added more actions to make it more interesting. And you can imagine that it gets fairly complicated quickly if we extend it more and more. And maybe that looks familiar to some of you with a different name. So if you close one eye and squint the other, it looks a bit like bounded model checking. Maybe I can convince you more by not using such a positive color, but a more negative color, and some more negative words. And maybe now it looks familiar to model checking. Okay, so in planning, we have those solvers, we call them planners, and they are given one of these planning tasks, and the output of them should be either a sequence of actions or a plan for this problem, or maybe there is no plan for this problem, and then it should say no plan exists. That's satisfying planning, but we are looking at optimal planning, and there it's similar, but the outputted plan should be of minimal cost. And in contrast to many other things we heard in these talks, there the complexity is p-space complete. So checking the individual plan that is in P, but the plan could be very long, exponentially long in the representation size of the planning task. And we can also represent as a planning task a bounded length Turing machine. And that should convince you that it is a p-space complete problem to find the plan or to confirm that no plan exists. Yes?
You say the plans can be exponentially long. On
yes.
What?
On the size of the encoding of the planning task.
So on the size of the transition relation? Or?
In the size of that.
Okay, thanks.
Okay, and now we're getting to the proof for optimal planning. Once I found an optimal plan, how could I convince you that it is optimal? And there's already some line of research on that. So as we said, checking the plan itself, that is somewhat fairly easy. And there are and the proof is the plan itself, that one exists. And we just check, oh, applying these actions one by one, does it really get us from the initial state to one of the goal states? And for that, there are already tools like val and inval. The other possible output is that the planner says no plan exists. For that, there is a line of research by Salome Eriksson, and she provided some unsolvability certificates that work on unreachability and unsolvability of different states and sets of states. And this line of research also extended for optimal planning. So they provided lower bound certificates that says, oh, no plan of 10 or less can exist. And if you also provide one plan of length 11, then you know, okay, that's an optimal plan. And in this work, we are tackling the third bullet point here in a different formalism. Okay, but for the proof of for this proof for low bound certificate, how can I convince you that no plan better than a cost of B exists? There we know that no plan with cost lower than B can exist if there is a property with the that fulfills the following 3 points. It is a property that holds for the initial state, and whatever action I apply, I'm still having this property. So it's an invariant or it's inductive. And the third point is that no goal state with cost lower than B is inside or has this property. So this corresponds to a separating set in the state cost pair graph. So here on top, we have the transition system that's used by the planning task. And below, we have some sort of time unrolling or cost unrolling of the states. And now I want to give you a proof that this planning task can't be solved with a cost of 2 or less. And for that, I'm showing you this set. And we can quickly confirm the 3 properties. The initial state with cost 0 is here, and it is inside the set. There is no goal with cost lower than B. There is one with cost B, that's okay, but lower than that, there's no goal state. And it is invariant, or it's inductive, and that we see because there is no outgoing arrow from the set. And that should convince everyone that no plan with costs 2 or lower exists. Okay, now we come to the logging part. And there we also have to look at how the planning system finds optimal plans. And there are different approaches. Some use a set encoding and put it to a set solver to try to find the plan. Others use symbolic search, so working with BDDs and looking at the sets of reachable states. But this approach uses an explicit search on the state space with the A-star algorithm. And the key idea of the A-star algorithm is that you have a set of considered paths, and you look at them and you take the most promising one, and you start to consider also its one-step continuations. The question is, what does promising mean in this context? For that, we look at the G value and the H value. The G value tells me how much resources did it take to get to this end of the path. And the H value tells me, oh, how much more resources are needed to get, are necessary to get to one of the goal states. And most promising then is the addition of those two values. And if it's minimal, then it's the most promising one. In this picture, I'm indicating it with the left number as the H value and the right number as the G value. And an important property for the heuristics is that they never overestimate. Otherwise, the A-star algorithm wouldn't be guaranteed to find the optimal one. Yeah, maybe I should have said this earlier. Heuristic means in the planning sense something else than in the SAT-solver sense, because a heuristic is for us a function that takes one state and maps it to one number that we can use as a goal distance estimate. Okay, so let us play this out in this case. So in the very beginning, we look at all the considered paths, and we start with the empty path starting from the initial state. And there we of course have a G value of 0. We didn't spend any resources yet. And we ask our heuristic, just some sort of subsystem in our planner, and it should tell us and estimate how much more is necessary. And since we need this promise that it never overestimates, we require from it also a lower bound certificate for this particular state. So it tells us the number 2, but we don't believe it without the proof. So it also has to provide one proof. For example, this set, which also has the nice properties. And it looks a bit different to the picture before, because earlier we set a lower bound of 3, and now we're looking at the 2, so more goal states are allowed in this set, in this invariant. Okay, and now this is our only considered path so far, so by definition it's the most promising one, and we look at its one-step continuations. I'm marking it this way to show, okay, we looked at this state, and therefore if we have different paths that also lead to this state, they are somewhat irrelevant as a path, because I have the path from here to there. This can't be better either. And that's the case for all higher cost variants of the state. Okay, and now I have 3 new paths that I consider. And for each of them, I have this G value, which is instantly computed. And I have these H values. And for each of them, I require proof again. And here again, we have this lower bound certificate. But this time it starts at a lower level because we have a different G value. And there you can again confirm the 3 properties. I have to have, I can do 2 steps without finding a goal state, and therefore it is a lower certificate for that. Similar for this one, I need at least 1 step to get to a goal, so it's a lower bound certificate for that. And for a heuristic value of 0, there I can put a trivial box around everything that has this cost layer and below or with higher cost. And I have a certificate for this as well. So now I continue with my search from these three paths. Which one is the most promising? It's the one with the h value of 0 and the g value of 1. So I'm expanding this one. And now I have a new path in consideration to this goal node, to this goal state. And it also has a heuristic value, which always has to be 1, otherwise it wouldn't be admissible. And for that, I would have some kind of trivial proof as well. And now I'm still deciding which one looks the most promising. And in this case, this one and this one look equally good. Because, and you can't stop already, because you could find a goal with a costly action very early. So you still have to keep searching, even though you consider one path that ends in a goal state, you still have to consider the others. But the tie breaking is on our side in this case. So we are expanding this goal state, and when we expand the goal state, then we are safe to stop. Then we know we found an optimal path through this state space. And now we have some, let's say, dangling certificates here in yellow, and we have those boxes about the states that we expanded. So we know that the states with higher costs are also not worth considering. And when we have those, we can do a union of all these sets and use this as our final certificate that we have a lower bound of 3 for this particular task. So that was the idea of the proofs and how we generate those proofs on the way while executing the algorithm. And now we're coming to the Pseudo-Boolean part. For that, we do a representation of this final invariant by a Pseudo-Boolean circuit. And we are proving the 3 properties for this invariant and those sub-invariants along the way. And when we have that, we can do a verification by having an encoding of the planning semantics into Pseudo-Boolean constraints. And when we combine this with the Pseudo-Boolean circuit for the invariant and the proofs about this invariant, then we can fire up VeryPB to verify for us that this invariant matches to this particular problem. And then VeryPB says, yes, I'm happy with it, and then we are happy as well. So how do we do this Pseudo-Boolean encoding of the planning semantics? So we are given for that planning task, and we use the state variables v as base blocks for all our Pseudo-Boolean circuits, together with some cost bits VC that encode the cost that we are considering at the moment. And we are also having prime copies of these variables and cost variables. And you can view this as similar to the set encoding with a horizon of 1. So the v variables, they represent the current state, and the v prime variables, they represent the successor state. And and the initial state, we represent this as a conjunction of all the variables that are part of the initial state together with excluding all the variables that are not part of the initial state. And for the goal, we do this similar, but for the goal, we just care about the things that are true, and things that are not mentioned in the goal condition, we don't care about them, whether they are true or false. So we have a smaller conjunction there. And now to the interesting part, the actions. How do we encode them? So I said for an action, we have a precondition. When are we allowed to apply this action? And it has to the precondition, so all the state variables that are part of the precondition, that should be part of the state, otherwise I'm not allowed to apply it. So this will be part of the conjunction. And for the successor state, it has to fulfill the post condition. So the things that I have as my add effect, that have to be added to the successors. The things that are in the delete effect, they are not allowed to be in the successor. But for all the others, I have the condition that they stay the same as they were. And additionally, I have this cost. So I want to express that when I apply this action, then the resources I have spent, they tally up. And there I can fairly straightforward encode this in this Pseudo-Boolean encoding, similar to what Matthew did in his talk, by having the value of the bit representing to its position. And then I can just subtract the one from the other to get this difference that should be corresponding to the cost of this action. And in the end, after I did this for all the actions, I'm having one variable that represents that I am doing a legal transition. And I'm doing a legal transition if one of the actions is applied. And then that's the encoding of the planning task, but we also want the encoding of the invariant. And for that, we build up a Pseudo-Boolean circuit based on the variables b and bc. And that is important that we are not using the primed version. This should be purely in the unprimed world. And this is built up until we have this representation of our invariant. And since we are only using non-prime variables, we can do a synchronized build-up of the Pseudo-Boolean circuit on the prime variables. And we call this phi prime. And they have to be synchronized for everything to work out. And once we have that, we can ask EuroPB to confirm that we have a proof for the three constraints that represent the three properties the invariant should have. That was that the initial state with a cost of 0 is part of the invariant. That if there is a goal state inside the invariant, the cost should be at least B. And for the inductivity, if we are in this state and we are applying any legal action to it, then we stay in this invariant. And once I have proven these three lemmas, and you trust me that phi and phi prime are synchronized, then you should also be confident that that this is a lower bound certificate.
So, but it's worth pointing out here that you don't get, so far in all talks we had, they end by proving 0 greater equal 1, and we have a proof by contradiction, and we're done, and this is not what you want here, right?
Yes.
So we'll end by proving these three clauses somehow, and then that should convince you.
Yes, exactly. And for the overall pipeline, you would have the planning task that you're trying to solve, and you put it into your planning system. And what's happening so far is that a planning system finds a plan, if one exists, and then this plan is validated that it actually is a plan and not some sequence of actions that wouldn't work out. But this wouldn't show me optimality. So what we want to add is that the planning system also outputs this lower bound certificate, and then we would forward this certificate, the check from this tool and the planning task into an optimality verifier, and it checks that the plan and the cost were, for example, 11, and then that the lower bound certificates certifies a lower bound of at least 10, and then the Pseudo-Boolean proof checker, EuroPB, would use this lower bound certificate with the planning task and confirm that this lower bound certificate is a correct proof. And now, what do we have so far? We have from the general framework the definition of a Pseudo-Boolean lower bound certificate and a Pseudo-Boolean encoding of the planning semantics. We are not done with the implementation, but we are working on it, and afterwards we would like to formally verify that. We are also working on theoretical relations to earlier approaches. And for the planning algorithms, there we have this general approach for heuristic search or explicit state search. And we explained how to do that for two heuristics. Those are the pattern database heuristic and the Hmax heuristics. We are working on an implementation on that as well. And we would like at some point to do this for more of the heuristics. As I said earlier, there are also other planning approaches like sub-planning and symbolic search, and for that it would also be great to do proof logging on them. But yeah, we haven't done that yet. And for more details, you can look at our archive or ICAPS paper. Yeah, and that's it. Thank you.
So, question for Simon.
So for SAT planning, you would need to verify that the encoding SAT is correct. This is all right.
For such, they're using tricks which makes it harder for optimal planning because they often do tricks where they can apply two actions in any order, and then they say, oh, we are applying them basically instantaneously. But this makes problem with the cost encoding. So there's more to do than just that.
So you mentioned, of course, you need to have a heuristic which is admissible. But, at some point, did you require to have monotonicity too? So that is a convergent, a consistent heuristic.
When we are doing H star with reopening, admissible heuristic is sufficient.
Any more questions? Otherwise, let's thank Simon again.
You do wrong connections.